Welcome back. Last time we met, we talked about work, power, and the energy of motion, kinetic energy. Now we know that moving objects store energy, and this can be dependent upon their mass and along the way, their speed squared. So it's an exponential relationship between the speed and the kinetic energy. The other type of energy we're going to look at is called potential energy. And this is energy that is stored. So it's an object that's not moving, because otherwise it would be kinetic, but it's energy that is stored up in an object due to its position. Now, that could be its position relative to something else, or it could be relative to its internal position, stuff on the inside of it as well. And we're going to investigate both today. So we're going to talk about the potential energy is the stored energy of an object. So while this object might be already moving, it doesn't necessarily have to be. It has energy stored in it because of its spot with respect to something else. And we're going to talk about that with respect to something else in a lot of great detail today. But give you an example. If you've ever held up an object really, really high, okay, it's not moving. It has no, energy, kinetic energy in it, but it has stored energy in it because if I drop it, that energy is going to cause it to move, to go down forward, okay? So gravity will do work on it and cause it to move. So an example would be like dropping an object. Or if you've ever seen like a pile driver, those objects that you use to smash like posts or piles into stuff. So that would be an example. Or if you're talking about a kid on a swing, if you pull yourself all the way up and then you let yourself go, when you pull yourself all the way up, that is when you have that potential energy. So kid on a swing at the top. So a couple different examples, and we'll investigate those a little bit more. But the first one we're going to look at is the example that I gave with both of those. It's called gravitational potential energy. And this is the energy, this is the main type of energy we're going to deal with. And it's the type of energy that an object has because of its position relative to the Earth. Okay? So let me give you an example. Like if I have an object, like if this is my ground level right here. So here's the ground. If I take an object and I put it up here, here's my object. It's going to have energy stored in it because of its height above the ground. I'm going to use H for height. And actually, let me just write out the word height right now. And we'll put the symbol in. That's H. Here's my object. It's going to have a mass. Okay. And obviously, there's an acceleration. Let's put that in. We'll go orange here. We also know that there's a force through gravity or acceleration through gravity pulling it down. So there's G down there as well. If we let this object go, it's going to start moving. So it has energy stored in it to be ability to do something. Okay? And so we can say that the formula for finding out the potential energy, I'll put this in black, potential energy, which the symbol is PE, is equal to the mass times the acceleration of gravity times the height. Now, if we think about this, this is, and I'm going to break this down just a tiny bit. If you look at mg, this is another way to write, and I'm going to put it in red, the force due to gravity, so F sub g. Now make sure you know that that's F sub g, not F times g, but that's the force due to gravity. Height, that's just another way of saying distance above the Earth, above the ground. I'll put this here, above ground. Ground level. Well, we talked yesterday that force times distance is equal to the work done. And so we can actually say that the work that you do on an object is equal, if I'm taking this object down here, and I'll put it down here, if here's where it was, down here like this, and I lift it up, I have to do work on it. The work that I do in overcoming that force of gravity becomes potential energy. And so I can say, and I'm going to scroll this up, actually I'll scroll this over just a touch. We can say that the work we do is equal to the change in the potential energy. Now, if you've been paying attention, this should make you go, wait a minute. Didn't just yesterday, didn't he tell us that the work was done on an object was equal to change in kinetic energy? And I did. And now I just got done telling you that the work done is equal to change in potential energy. So am I a big fat liar, or is there more to it? Let's go with option 2. Turns out there's more to it. The work you do on it will equal the change in the energy of the object. The type of energy change depends on what you did. When I did this here, when I took this ball and I lifted it up to that height, I exerted a force on it over a distance. I did work on it to overcome gravity, but my initial velocity was 0. My final velocity was 0. It changed the height. So the work that I did caused a change to the potential energy. Energy to be stored in that object. If I take a ball and I throw it, I exert a force on it over a distance. It causes it to accelerate, to change its velocity, go from nothing to something. So the work I did there was equal to the change in kinetic energy. And so we're going to talk about this a little bit later on, okay? But just know, I'm actually going, you know what? I'll put it in here right now because this is kind of crucial. The work you do on an object will always equal its change in energy. And I'm going to highlight that because that is crucial. That's very, very important. You're going to hear me say a lot. Work done equals a change in energy. It could be potential. It could be kinetic. It could be both. And so we need to take that into consideration. Now, there's another thing on here too, and I'm just going to mention, I'm going to define it today, and then we'll go into more detail tomorrow in class. But base level, this is where we define. And I put we in quotation marks because really it's you. It's your choice. It's where we define the potential energy to be 0. It's where are we going to start measuring that height, that h that we had before, where are we going to start measuring from? Because at the bottom there, that means if it's sitting right here, if that's my base level, then when I measure that height, I'm going to measure from there. That means when it's at that spot, my potential energy is going to be 0. But this also allows us to find out that if we go below it, let's say we come down here, and I'll put it in rainbow. Let's say my object is down here. I'm a negative height from my base level. I can have a negative potential energy. You can't ever have a negative kinetic energy, but you can have a negative potential energy. So something neat, something cool. But we'll talk about more about base level tomorrow in class. Now, the other type of potential energy we're going to talk about is called elastic potential energy. Double check, make sure I'm going too far. Oh yeah, we got a couple there. These are energy that we see every day. It's what's stored inside a spring. So, and I don't have one on me, but if I'll get one tomorrow for class. But if I take a rubber band, oh wait, hang on. And you just all saw the fact that I am wearing shorts and not pants today. So apologize for that. But it's very warm, okay? But here's my spring, okay? If I try and pull this apart, again, its initial velocity is 0, its final velocity is 0. I have to do work on this in order to pull it apart. When I do work, there's energy that's stored into it. How do I know if I let it go? It goes flying across. And so this is energy that's stored. Now, there's no change in position relative to the ground here, but there's a change in its internal position. I stretched it out. And so there's a force there. Okay, so a spring is stretched compressed. It will do work to try and return back to its original position. Okay, so we can say that the potential energy stored in a spring, so PE sub S, potential energy stored in a spring, is equal to the work done in compressing the spring. I'll write that out. Work done in changing the spring length. Now, there's a special formula here, and we're going to discuss it in more detail tomorrow. But if we talk about the potential energy stored in a spring, the equation, you'll find this in your reference tables, is equal to 1/2 K x squared, where K is known as the spring constant. It's how difficult or how much force it takes to stretch a spring a certain amount. X is how far the spring changes its length. And I usually go with, oh, you're going to stretch it, but not all. Some springs you compress, changes its length. And the reason for this, well, we're actually going to investigate this formula in greater detail when we get into the beginning of waves. So for right now, all you're going to have to know is how to solve problems with this equation. And we're going to discuss why is it the 1/2? Why is the X? We're going to discuss that at the beginning of chapter 12. So we're going to stop here. We're going to do lots of sample problems with this tomorrow and make sure we can know the difference between potential energy, kinetic energy, how work factors into all of it. But then we'll get finished with that. So everybody have a great night. We'll see you later. Bye.